Somewhere, hidden within the intense glare of our sun, a rock is slowly being baked to pieces. We have never seen it. We have never photographed it. We do not know its precise size, its exact shape, or its specific orbit. Yet, thanks to a peer-reviewed paper published just 5 days ago, we now know it is real. This object is actively shedding fragments of itself into Earth's path, and for the last 3 weeks, we have been flying through its trail of cosmic crumbs. This revelation may finally offer the first scientific explanation for the swarm of fireballs that Calm Space has been documenting since March, an event the American Meteor Society just confirmed as a 4.5 Sigma anomaly. While 2 visible asteroids are set to skim past us closer than the Moon in the next 24 hours, they are a secondary event. The true story lies with the one that remains invisible, and what its discovery implies about other hidden objects is a part of the narrative that is only just beginning to unfold. Within the next 24 hours, a pair of asteroids will sweep past Earth, and yet neither of them is the central story. This is a detail that runs counter to our instincts about how space news typically works. Ordinarily, when an object the size of a building ventures closer to us than our own Moon, that becomes the headline. It is the event we are told to watch, the kind of news that might trigger a late-night notification on our phones. But as I record this, 2 such objects are about to do exactly that, back to back, within a single rotation of our planet. And these 2 visible travelers are not what we truly need to be talking about. They are a distraction, drawing our gaze while something far quieter and more consequential unfolds just out of frame. Between Saturday morning and Sunday afternoon, 2 distinct asteroids are set to slip past Earth inside the orbit of the Moon. The first is named 2026 HQ, and it will cross our path at a distance of 0.43 lunar distances. Following it is 2026 HJ, which will approach even closer at 0.3 lunar distances. For those who prefer more terrestrial units, that translates to about 160,000 miles for the first pass and roughly 115,000 miles for the second. In cosmic terms, it is the equivalent of 2 strangers brushing shoulders in a vast, dark hallway. In human terms, it is still a very long way away. You are not in danger, your pets are not in danger, and your plants will be perfectly fine. But here is where the narrative begins to take a curious turn. Both of these asteroids were discovered only weeks ago, not years or decades, but mere weeks. At the start of this year, they were entirely absent from our astronomical catalogues. They were not on anyone's radar, nor were they being tracked, modeled, or predicted. Then, suddenly, within a very narrow window of observation, both of them appeared in our surveys. They were each flagged for a close approach, and now they are gliding past us, as if they had always been on the cosmic schedule. From the universe's perspective, they always were. It was simply our awareness that had yet to catch up. Now, before your pulse climbs too high, it is important to ground these events in some crucial context. Sublunar flybys, meaning asteroid passes that occur closer to Earth than our Moon, actually happen multiple times every month. Statistically speaking, they are routine. They are part of the cosmic background noise. Our orbital neighborhood is a messy place, full of small bodies tumbling along their own paths. And every few weeks, one of them wanders into our address. Most of the time, these flybys go unnoticed by the general public, drawing the attention of only astronomers and automated tracking systems. We rarely hear about them because the mathematics confirms they are safe, and the math is almost always right. So, 2 asteroids passing us within 24 hours is not, in itself, a crisis. It is not even particularly unusual on its own. What makes this moment so compelling is the timing. This is because 5 days ago, buried within a peer-reviewed paper in the Astrophysical Journal, a NASA scientist quietly announced something that most of the news cycle has not yet caught up with. It turns out that Earth has spent the last 3 weeks moving through the debris trail of another asteroid entirely. This is not one of the 2 objects we can see, but a third, hidden one. It is an object that has never been directly observed, is not listed in any catalogue, and has no official image, confirmed orbit, or identification number. As a result, there is no way for it to be tracked from the ground. This is because the object, whatever it may be, resides in a place we simply cannot look. It lives inside the blinding glare of the sun. This single fact changes the entire story. While we have been watching the 2 visible asteroids march closer to us, a third, completely unseen object has been shedding material directly into our path for weeks. We are only now becoming aware of its existence because that material has been burning up as meteors in our sky. This is what today is truly about. It is not about the 2 rocks that are going to sail harmlessly past us. It is about the one we missed. It is about the one that never showed up on any telescope because it has been hiding in a blind spot we have never been able to penetrate. And it is about the fact that we are only now, in the last few days, starting to piece together the indirect evidence that it exists at all. This brings us to another thread that runs through this entire story, the fireball anomaly. Since March, the American Meteor Society has been logging an unusual increase in bright meteors, long-duration fireballs, and even physical meteorite recoveries. By the time the first quarter of 2026 was over, they had classified the anomaly at 4.5 sigma. In statistics, this means there is roughly a 1 in 200,000 chance that this event occurred randomly. That is not a fluke. It is a signal. That signal has been building for weeks with no confirmed cause until now. With this paper, and with this hidden object, we may have finally been handed the first peer-reviewed hypothesis to explain it. And running just underneath all of this, racing ahead of the formal science, a viral narrative has already begun to form. You may have encountered them online posts, asserting that Earth is passing through a dense field of cosmic debris, or videos forecasting an imminent disaster. The comment sections often fill with apocalyptic speculation. The reality, however, is far more compelling than the alarm, but the alarm spreads faster because it offers simple certainty, whereas the truth demands we embrace a degree of ambiguity. This creates a central tension to consider. Are we merely witnessing a series of unrelated events happening to occur in close succession? Is it just a coincidence that 2 asteroids make close passes, a new scientific paper is published, and a surge in fireball activity is recorded, all while our human tendency for pattern recognition fills in the gaps? Or could these be signs of a single, vast system, one that is slowly revealing itself through its various effects, and allowing us to perceive a population of objects we have been missing all along? The most important question is not whether any of these specific objects will harm us tomorrow. They will not. Instead, the crucial issue is one of detection. How much of the cosmic environment that shapes Earth's immediate neighborhood are we actually capable of seeing? And how much is moving through our corner of space, past our planet, and into our upper atmosphere, completely uncatalogued, unphotographed, and unnamed? In a strange twist, the objects we can see are the ones that will simply pass by and leave. It is the object we cannot see that has been actively interacting with our world, feeding meteors into our sky for 3 consecutive weeks. Over the course of this journey, we will follow this trail of evidence backward, from the flashes of light in the sky, to the debris stream that caused them, to the invisible parent body, and into the observational blind spot where it resides. We will explore the nature of rock comets and the promise of sunward-facing telescopes. We will look at the work of a NASA scientist and a remarkable dataset collected across 4 continents. We will consider what all of this means for planetary defense and for our understanding of the space we have already been traveling through completely unaware. The uncomfortable truth is that we are not reacting to what is approaching Earth. We are reacting to what Earth has already been moving through, unseen. And that realization changes the entire conversation. The two most visible actors in this story are the asteroids making their flybys. But before we begin to chase the ghost in this cosmic machine, we must first understand why these two observable rocks are, in many ways, the least interesting part of the narrative. While close approaches are routine, this particular timeline is not. In a very real sense, these asteroids are like stage lights. They serve to illuminate the scene and draw our attention to the sky. They make us look up. But they are not the main performers. They are not even part of the same production. The first to arrive is designated 2026 HQ. This object will pass at a distance of 0.43 lunar distances, which is equivalent to roughly 160,000 miles from the surface of our planet. This is comfortably farther away than the Moon, yet it falls well within the threshold that astronomers use to classify an event as a close approach. 2026 HQ is estimated to be a small to mid-sized asteroid. It is large enough that it would cause serious localized damage if it were to strike Earth. But it is small enough that its trajectory never actually intersects with our own. Its passage is clean, and its orbital geometry is understood well enough for us to know with confidence that it poses no threat. It will approach, it will recede, and within a week, it will fade from most news cycles entirely. The second act of this celestial drama is 2026 HJ. This asteroid is set for a tighter approach, coming within 0.3 lunar distances, or about 115,000 miles. It is moving at a velocity of approximately 6.48 kilometers per second relative to Earth, a typical speed for an object of its class, which translates to about 14,500 miles per hour. In terms of its size, comparisons to the Chelyabinsk meteor become relevant. That object, which exploded over Russia in 2013, was the one that shattered windows across an entire city, leaving people with unexpected injuries from flying glass. The Chelyabinsk impactor was about 20 meters across, and 2026 HJ is believed to be in a similar size category. If it were on a collision course, we would be anticipating an airburst event, not a global catastrophe, but a serious regional incident. But, like its companion, 2026 HJ is not on a collision course. Its trajectory is safe. The mathematics are clear. The sky above you will not change because of its passage. Here, however, is where a sense of unease should begin to settle in. For all our tracking, neither 2026 HQ nor 2026 HJ has been studied with detailed radar imaging. We possess no high-resolution models of their shapes. We do not know their rotation rates or their surface compositions with any precision. We know that they exist, we have an approximation of their size, and we know their destination. That is the entirety of the file. And this file was only opened a few weeks ago, because that is when they were first detected. This is what is known as the detection lag, the gap between an object entering our observational range and the moment we actually register its presence. For these two asteroids, that gap closed just in time. We saw them, we tracked them, and we confirmed they were safe. The system worked, but only in the most minimal sense. This is where the numbers should start to give you a sense of the vastness of the unknown. NASA estimates that there are let that figure sink in for a moment. 15,000 objects large enough to erase a city from the map. These are objects that, if they were to strike the ocean, could generate tsunamis capable of reshaping coastlines. And as of right now, we have no idea that they exist. That figure only accounts for the larger objects. If you scale down to the Chelyabinsk class, those in the 2-0-meter range, the estimated population of undiscovered bodies rises into the hundreds of thousands, and possibly more. These objects are so difficult to find because they are small, dark, and fast-moving. They reflect very little sunlight, which makes them extraordinarily challenging for our telescopes to pick up against the blackness of space. Detecting them often comes down to a matter of luck. You have to happen to catch them in a specific orbital configuration, one where they are distant enough to be tracked over time, but just close enough to be visible at all. It is a delicate balance, and one that is not often met. This brings us to a concept that may help to make sense of this entire story, a phenomenon we might call routine invisibility. The idea is simple. For the vast majority of their existence, the vast majority of these objects are simply not visible to us. They may be in parts of the sky our instruments cannot reach, or they may be too small for our sensors to detect. Sometimes their very motion hides them from our cameras. They exist, they are active, and they influence our orbital environment, but for all observational purposes, they are invisible. This creates a profound psychological mismatch, which helps to explain why moments of discovery like this one can feel so jarring. We are not seeing something new appear out of nowhere. We are simply catching a brief, fleeting glimpse of what is, and always has been, there. For a scientist, the passage of asteroids HQ and HJ this past weekend is entirely routine. Events like this occur with enough frequency that they barely cause a ripple within the planetary defense community. It is, for them, simply another day at the office. Yet for the public, learning that 2 previously unknown asteroids will graze past Earth within a single 2-4 hour period can sound like a scenario from a disaster film. The event is, in a fascinating paradox, both completely ordinary and deeply shocking, and both viewpoints are valid depending on one's perspective. Now, it is essential to clarify a critical point, as the details are easy to confuse. The asteroids HQ and HJ have no connection to the hidden object that will be the focus of our journey. They are not part of the M2026A1 debris stream, nor are they linked to the fireball anomaly or fragments of the rock comet we are about to explore. They are simply unrelated celestial travelers, passing by at the same moment a much deeper story is coming to light. Their true value to this narrative lies not in what they are, but in what they represent. If 2 objects, unknown to us just a month ago, can approach Earth so closely that we only find them in time to confirm their safety, what does that suggest about the completeness of our celestial catalogue? It tells us that our map of the solar system has significant gaps. It confirms that objects can, and do, emerge from observational blind spots with little to no warning. For bodies of this size and smaller, discovery often pushes the very limits of our capabilities, sometimes occurring just days before their closest approach. This is precisely how the hidden asteroid at the heart of our story has managed to elude detection for so long. It resides in one of those blind zones, not a temporary one, like that which concealed HQ and HJ, but a far more specific and systematic one. It exists in a place we have been unable to properly search, inside the blinding glare of the Sunday. And while we have been watching the 2 objects we can see, this other one has been doing something else entirely. It has been quietly shedding pieces of itself directly into our planet's path. The scientific paper that revealed this story was published 5 days ago, and if you do not follow planetary science press releases, you almost certainly missed it. The vast majority of people did. It failed to trend on major platforms or break into the mainstream news cycle. After its publication in the Astrophysical Journal, one of the most respected peer-reviewed journals in its field, it simply sat there, waiting for someone to grasp the significance of its findings. The paper's author is Dr. Patrick Schober, a researcher based at NASA's Johnson Space Center, whose work occupies a fascinating niche. Dr. Schober specializes in tracing the orbits of meteors to identify their parent bodies and the streams they belong to. It is a field of cosmic forensics. Every meteor that streaks across our sky was once part of a larger object, and that parent object followed its own distinct orbit around the Sunday. If you can meticulously reconstruct a meteor's trajectory back to its origin, you can begin to map the sources of this celestial debris. In this paper, Dr. Schober undertook a monumental task. He analyzed a massive dataset gathered from global meteor monitoring networks across Canada, Japan, Europe, and California, searching through it for statistical clusters. At its most fundamental level, a meteor shower is nothing more than such a cluster, a group of meteors that all share strikingly similar orbital parameters, proving they originated from the same source. The famous Perseids, for example, are a cluster linked to Comet Swift-Tuttle, while the Leonids trace back to Comet Tempel-Tuttle. Every major shower has a known parent, but when Schober completed his analysis, he uncovered something entirely new. He found 282 meteors, recorded across multiple independent networks, that shared orbital characteristics so closely that the probability of the grouping being a random coincidence was statistically insignificant. These were not stray background meteors, nor were they remnants of any previously known showers. This was something else, a pattern that had never been identified. Because it was a new discovery, it required a formal designation. The stream was named M2026A1, where M signifies a meteor stream, 2026 marks the year of confirmation, and A1 denotes it as the first new stream identified this year. It is a clinical name for what is proving to be a very strange object indeed. What Dr. Schober had found was not just a new shower, but one whose properties pointed back to a parent body that has never been observed. The shared orbital parameters of the meteors told a truly unusual story. The stream's perihelion, the point in its orbit where it passes closest to the Sun, was calculated to be approximately 0.22 astronomical units. To put that in perspective, 1 astronomical unit is the distance between Earth and the Sun, meaning these fragments travel to within 22% of that distance. This is an extraordinarily close solar approach, even closer than the planet Mercury ever gets. At that range, the solar heating is absolutely brutal. Surface temperatures on any object orbiting so near the Sun would soar to hundreds of degrees Celsius. Rock would become stressed and fractured, and any volatile materials would be violently cooked away. An object that repeatedly makes such a close pass is subjected to immense thermal abuse. This detail is critically important because most meteor streams derived from asteroids do not have perihelion values this extreme. When you find a stream with an orbit that dives this deep into the inner solar system, you are likely looking at something special, an object that spends a portion of its life in a zone where the physics becomes truly strange. Furthermore, the radiant of the stream, the point in the sky from which the meteors appear to originate, was located near the celestial boundary of the constellations Virgo, Corvus, Libra, Centaurus, and Lupus. This information is another vital clue, as it constrains the geometry of the source. A parent body cannot have just any orbit. It must intersect Earth's path in a very specific way to produce meteors that appear to radiate from that precise direction in the sky. When Dr. Schober worked the mathematics backward, combining all of these clues, he discovered that the parent body responsible for this stream must follow a unique orbit, one that takes it perilously close to the Sun before crossing Earth's path. That orbit could now be calculated. The object's general properties could be inferred from the debris it left behind, and yet, the object itself has never been seen by any telescope. Let that profound implication settle for a moment. All the evidence points to a ghost in the solar system, an object whose existence is known only by the trail it leaves behind for us to find. We have confirmed the presence of an asteroid not by seeing it, but by tracing the trail of debris it leaves behind. This remarkable process is what one might call reverse detection, an approach that inverts the standard method of discovery in space. Normally, we begin with an observation, a point of light in a telescope from which we calculate an orbit, predict its effects, and then watch to see if our models are correct. Observation comes first, followed by inference. Reverse detection flips this sequence entirely. It begins with an observed effect, works backward to identify the cause, and ultimately allows us to infer the existence of something we have never directly seen. The philosophical weight of this method is greater than it might initially appear. We are declaring the existence of a physical object based solely on the pattern of its consequences. There is no image, no radar echo, no spectroscopic signature from the body itself. All we have is the river of dust and rock it has left in its wake, which happens to be flowing through our small corner of the solar system. This is not unprecedented in science. Inference is a powerful tool. We have deduced the presence of exoplanets from the subtle wobble they induce in their parent stars, and the existence of dark matter from the anomalous rotation of galaxies. We even infer subatomic particles from the invisible tracks they leave in our detectors. When the evidence is strong enough, inference is an entirely valid form of detection. In this case, the evidence is indeed compelling. A total of 282 meteors, all pointing back to a single origin point on orbits that cannot be explained by any known object, constitutes a clear signal, not mere cosmic noise. But for all its power, inference can only tell us so much. It confirms that something is there, but it cannot reveal its color, its rate of spin, what its surface looks like, or how stable it is. Answering those deeper questions requires direct observation, a task that, for this particular object, is currently impossible because of where it resides in space. This leads to a fundamental puzzle. How does a simple rock in space create such a trail? The mechanism behind this phenomenon becomes clearer when we distinguish between asteroids and comets. Comets are the usual source of meteor showers. As a comet journeys through the inner solar system, the sun's heat causes its ices to sublimate, transitioning directly from a solid to a gas. This venting of gas carries dust with it, and over time, this process leaves a long debris trail along the comet's orbit. When Earth's own orbit intersects that trail, we experience a meteor shower. Asteroids, however, are not supposed to do this. They are understood to be dry, rocky bodies that lack the volatile chemistry of comets, which prevents them from shedding material in the quantities needed to form visible streams. It seems our understanding of these objects may need to be revised. The textbook definition of a comet centers on its composition, a mixture of ice, frozen water, frozen carbon dioxide, frozen methane, and frozen ammonia. These are the volatile compounds that remain solid in the frigid outer solar system where comets form. As a comet swings inward toward the sun, these ices begin to sublimate, meaning they turn directly into gas without passing through a liquid state. The escaping gas then drags dust from the surface. And this combination of gas and dust is what creates the glowing coma and long tail that give comets their iconic appearance. By contrast, the classic definition of an asteroid paints a very different picture. Asteroids are rocky bodies, fundamentally dry, and are considered leftover debris from the formation of the inner solar system, where temperatures were far too high for ices to condense in the first place. An asteroid, in principle, should simply remain a passive rock. It is not expected to shed material from its surface, grow a tail, or produce a meteor stream. And yet, for the past few decades, astronomers have been quietly documenting a new class of objects that defies this simple categorization. These objects are classified as asteroids because they are rocky and lack obvious signs of ice, but they nevertheless behave like comets. They generate dust, display signs of activity, leave behind trails, and are the source of meteor streams. The question of why they do this has become one of the more fascinating puzzles in the study of small celestial bodies. The answer, it turns out, is a process known as thermomechanical stress. While the term sounds complex, the concept is intuitive. If you have ever dropped a cold glass into hot water or seen a ceramic plate crack under a sudden temperature change. When rock is heated, it expands. When it cools, it contracts. If this cycle is repeated over and over again, particularly in the presence of a steep gradient, meaning one side is hot while the other is cold, internal stresses build up until the rock begins to crack. Fractures form, material flakes away, and pieces break loose. Now, imagine this process applied to an asteroid with an orbit that brings it to a perihelion distance of just 0.22 astronomical units. Each time it swings close to the Sun, its sunward face is baked to temperatures that can exceed 700 degrees Celsius, while its opposite face remains much cooler. This creates an enormous thermal gradient across the object. This cycle of extreme stress happens on every orbit, repeating for hundreds, thousands, or even tens of thousands of years. Under such conditions, rocks do not simply endure, they crack, they spall, and they shed their outer layers. The object is slowly being disassembled by the Sun itself. There is even a second mechanism that contributes to this process, and it involves sodium. Sodium is a metal that, under extreme temperatures, can vaporize directly from the surface of a rock. When the sunward face of one of these objects gets hot enough, sodium atoms begin to boil off. This sodium vapor creates its own form of gas pressure, which can help lift small particles of dust and rock away from the surface. It is not the same mechanism that drives cometary activity, which relies on water ice, but the outcome is remarkably similar. Material is ejected from the surface, a dust trail is formed, and eventually, a meteor stream is born. The quintessential example of this type of object is 3200 Phaethon. Phaethon is one of the most peculiar bodies in our solar system. It was classified as an asteroid upon its discovery due to its rocky spectrum and lack of obvious ice. However, it has a perihelion distance of only 0.14 astronomical units, bringing it even closer to the Sun than the hypothetical parent of the M26A1 stream. Despite being an asteroid, Phaethon is the confirmed parent of the Geminid meteor shower, which is one of the most reliable and spectacular showers of the year. For decades, the Geminids were a mystery. Every other major meteor shower had a known comet parent, but the Geminids did not, leaving astronomers searching for an explanation that this strange, rocky comet now provides. Following the trail of celestial breadcrumbs, astronomers eventually identified an asteroid named Phaethon. After calculating its orbit, they made a stunning realization. The asteroid and the Geminid meteor shower traveled along the very same path. Phaethon was the source. This discovery presented a fascinating puzzle, as an asteroid was now known to be feeding one of the most brilliant meteor displays of the year. But how was this possible? Years of subsequent observations revealed the answer. Phaethon is a rock comet. It is an object that shares characteristics with a comet, namely the production of a debris stream, but the mechanism is entirely different. Instead of ice sublimating into space, Phaethon's activity is driven by intense thermal stress and the vaporization of sodium. When observed near its closest approach to the Sun, or perihelion, Phaethon exhibited faint signs of activity, with emissions dominated by sodium, not water. Crucially, the quantity of dust that Phaethon sheds during any single orbit is remarkably small, far less than a typical comet would release, and in fact, too little to explain the entirety of the Geminid stream within any plausible time frame. This suggests that Phaethon is not experiencing a single, massive outgassing event. Instead, it is slowly leaking, losing minute amounts of its mass with every passage by the Sunday. These losses accumulate over thousands of years, meaning the Geminid stream is not the aftermath of a catastrophic event, but the product of a gradual, consistent breakdown over geological timescales. This understanding of Phaethon provides a powerful template for what might be happening with the hidden parent of meteoroid M226A1. The source is almost certainly a rock comet of a similar class to Phaethon. It might be smaller, perhaps younger, or follow an orbit that has evolved differently, but it likely operates on the same fundamental principles. It swings in perilously close to the Sun, where it endures brutal thermal stress. As its surface heats, sodium vaporizes, and this process lofts small particles free from its body. Under the relentless pressure of this thermal cycling, larger fragments may occasionally break away. Over vast stretches of time, this slow erosion forms a trail of debris along its orbit, a trail that our own planet eventually intersects. This model of slow disintegration, however, raises profound questions about our ability to find such an object. For astronomers, the implications for detection are significant, and this brings us back to the challenge of directly observing this elusive body. Rock comets generate very little dust when compared to their icy cousins, making their activity far more subtle. The enhancement in their brightness near perihelion is minor. If you were to point a telescope at Phaethon when it is far from the Sun, it would appear as just another dark, unremarkable asteroid. From its appearance alone, you would never suspect that it was the source of a meteor stream that lights up our skies with hundreds of fireballs each December. In practical terms, this means that our standard strategies for finding comets, which are optimized to detect bright comas and long, dramatic tails, are ill-suited for discovering rock comets. These objects are dim, they are rocky, and they reflect very little light. To make matters worse, the faint activity that would betray their nature, the subtle vaporization near perihelion, occurs in a region of the sky that is physically impossible for us to observe from the ground. A secondary process, known as rotational spin-up, can also accelerate this disintegration. As an asteroid sheds small particles asymmetrically from its surface, these ejections can impart a tiny amount of torque on the parent body. Over immense periods, this cumulative torque can cause the object to spin faster and faster. If it begins to rotate rapidly enough, the resulting centrifugal force can exceed the object's own weak gravity, causing it to start tearing itself apart. This is currently the leading theory explaining why some rock comets ultimately fragment, and it is one of the key mechanisms responsible for producing the smaller meteoroids that populate these streams. So, when Earth passes through the M226A1 stream, what we are witnessing is the cumulative result of this slow, multi-mechanism process of decay. We are not intercepting the debris from a single dramatic event, but rather material that has been shed over centuries, or even millennia. From an object that has been quietly cooking itself to pieces in the sun's glare for longer than human civilization has existed. This process of a rock comet's decay is ongoing, slow, and steady, and for our search, it critically occurs in a place we cannot easily look. This raises a question that by now should feel quite significant. If this object is actively producing debris, and has been doing so for a very long time, and if we can calculate its parent orbit, its radiant, and its perihelion, why has no telescope ever managed to see it? The answer lies in geometry, and in a form of blindness that is inherent to how we observe the cosmos. We are not missing this object because of a lack of effort. We are missing it because the very design of our instruments and the position of our own planet mean we literally cannot look where it resides. To grasp why we cannot see the parent of M226A1, we must first explore the geometry of observation. From the surface of Earth, this geometry is surprisingly restrictive, a fact that becomes clear once you consider the single greatest constraint on our view: the Sun is overwhelmingly bright. Any object that appears near the Sun from our line of sight is simply washed out by its brilliance. The Sun is not merely a source of light, it is an overpowering one. It is so luminous that even several degrees away from its disk, our sky glows with scattered light that drowns out nearly everything else. This is the simple reason we cannot see stars during the day. It is not that the stars have vanished, it is that the Sun's light, scattered by Earth's atmosphere, creates a luminous veil that no distant star can penetrate. Astronomers use a measurement known as solar elongation to describe this relationship. It is simply the angle between the Sun and an object of interest as seen from Earth. If an object has a solar elongation of 180 degrees, it sits directly opposite the Sun in our sky. This means it is visible only at night, in the darkest and clearest conditions, making it easy to observe. When an object has a solar elongation of 90 degrees, it is at a right angle to the Sun, placing it in the twilight hours, where it remains generally quite observable. However, as the solar elongation drops below approximately 45 degrees, conditions become increasingly difficult. The object is now too close to the Sun in the sky, and can only be seen in a narrow window just before sunrise or just after sunset. Once that angle shrinks below about 20 degrees, observation from the ground becomes effectively impossible. The object is lost in the Sun's glare. And herein lies the core of the problem. Objects on orbits that pass extremely close to the Sun, which is precisely the definition of a rock comet's path, spend the majority of their time at these low solar elongations. Consider an orbit with a perihelion of just 0.22 astronomical units. Such a path dips far inside the orbit of Earth itself, meaning that from our perspective, the object will almost always appear near the Sunday. This is the fundamental paradox. The very process that makes the object interesting, its fiery dance with the Sun, is what keeps it hidden from our view. It is concealed not in the dark depths of space, but in the brilliant glare of its own star. For a significant portion of their journey through space, certain objects remain almost completely invisible to us. When their orbits bring them closest to Earth, they are often on the far side of the Sun, or appear so near to it in our sky that they are lost in its brilliant glare. They are, for all practical purposes, hiding in plain sight. This is not a fleeting issue that resolves as an object continues its path. It is a structural consequence of orbital mechanics. The very geometry of their orbits means that objects with low perihelia, their closest approach to the Sun, spend a disproportionate amount of time within this solar blind zone. It's a profound observational challenge, and it explains why entire classes of objects, like rock comets, were only recently identified, despite having likely existed for millions of years. We were simply unable to look where they spent most of their time. To understand what this means, imagine our planet tracing its annual path around the Sunday. From our vantage point, a vast cone of vision extends outward, defining the region of the cosmos we can observe during the night. While this cone is wide, it does not encompass the entire sky. There remains a wedge-shaped area pointing directly toward the Sun that is permanently inaccessible to our ground-based telescopes. This is no small gap. It is an immense volume of space where many near-Earth objects travel. Crucially, it contains the entire orbital region that objects with low perihelia must pass through on their inward and outward journeys. This observational blind spot is a permanent and fundamental hole in our coverage of the inner solar system, and until very recently, there was nothing we could do to close it. NASA has long acknowledged this vulnerability. The detection gap for objects in sunward orbits stands as one of the most significant limitations of our current planetary defense surveys. As a result, the catalogue of near-Earth objects we have compiled is inherently biased, favoring bodies that spend most of their time in regions of the sky we can actually see. Objects that primarily reside in this sunward territory are systematically undercounted in our census. By the very nature of our instruments, they remain invisible to us. This raises a troubling question. How much larger might the unseen population be compared to the one we have catalogued? We cannot know for sure, because it is impossible to measure what you cannot detect. However, estimates derived from modeling studies suggest that this sunward blind zone could harbor a substantial fraction of the total near-Earth population. The numbers could be staggering, potentially including dozens or even hundreds of objects in the rock comet class alone. This is precisely why the discovery of the 2026 A1 meteor stream is so important. It is more than just a new shower. It is tangible proof that the blind spot is actively populated. It provides compelling evidence that the unseen population is not merely a statistical abstraction, but contains real, dynamic objects that are influencing Earth's environment today. The hidden parent body of this stream has been orbiting in that blind zone for an unknown length of time, shedding material with every close pass of the Sun and slowly building a trail of debris that our planet just happened to cross. The indirect detection of even one such object carries powerful statistical implications. If a single one exists, it is almost certain that many more do as well, making this a representative case rather than a unique one. The question then is no longer times if times the blind zone contains objects we now know that it does. The critical questions become: how many are there? How active are they? And are any of them on orbits that could eventually produce something far more dramatic than a simple meteor stream? This is the challenge that the NEO-SURVEYOR mission was conceived to address. NEO-SURVEYOR is a NASA mission specifically designed to overcome the sunward detection gap. The spacecraft is being engineered to operate in the infrared part of the spectrum. This is a crucial detail because, unlike detection in visible light, which relies on reflected sunlight, infrared astronomy picks up the thermal emissions of the objects themselves. Every object warmer than absolute zero radiates heat in the infrared. From the right vantage point and in the correct orbit, far from the warmth of Earth's atmosphere, a telescope can detect this thermal signature even from objects obscured by the sun's glare. The plan is to place the spacecraft at the Earth-Sun Lagrange point 1, also known as L1. This point of gravitational stability sits about 1.5 million kilometers from us, in the direction of the Sunday. From this unique position, NEO-SURVEYOR will be able to look outward and survey the inner solar system, finally illuminating the blind zone that our telescopes on the ground cannot reach. It is the observational equivalent of stepping away from a blinding light source, allowing your eyes to finally adjust and see what was hidden in the glare. The problem, however, is one of timing. NEO-SURVEYOR has not yet launched, and its current schedule places its departure no earlier than 2027. This means that for at least another year, and possibly longer if there are delays, the blind spot will remain blind. For now, we are left to reconstruct the unseen population indirectly, using methods like the analysis of meteor streams. This is the only way we can study the sources without the instruments needed to see them directly. Consider the position this leaves us in. Our best current understanding of what lies in the sunward zone comes not from observing it, but from studying what it sends our way. We are like forensic investigators working a case where we can examine the evidence, but are barred from the scene itself. We can see the debris trail, measure the resulting meteors, and calculate the orbit to infer the properties of the parent body. But we cannot lay eyes on the source, not yet. And in the meantime, the blind zone continues its silent work. Material keeps arriving, new streams are gradually built, and parent bodies continue to shed their mass, all while Earth moves through the orbits of objects we will not see until we launch a telescope that can stare at the sun without flinching. This brings us to a question that was addressed almost in passing within Schober's paper, but one that proves to be enormously important. Before this story became one of rock comets slowly shedding material over centuries, many people, including some scientists, had suspected a very different mechanism might be responsible. They envisioned a process that was far more dramatic and sudden, one that could theoretically produce a stream this significant in a much shorter period of time. That mechanism was tidal disruption, and when Schober went searching for its signature in the data, he did not find it. Sometimes, one of the most vital contributions a scientific paper can make is to tell you what is not there. We tend to focus on discoveries and confirmations on the things that positively show up in the data. Yet in science, a negative result, The finding that something you expected to see did not happen can be just as illuminating as a positive one. It refines our understanding by showing us which paths not to take. Within Schober's paper lies a crucial negative result, one that has been largely overshadowed despite its importance. This finding directly challenges one of the most compelling narratives about the meteor stream circulating online. This popular story suggests that a very large asteroid, perhaps in an unstable orbit, ventured too close to the Sun or a planet and was torn asunder by immense gravitational forces. The result would have been a massive cloud of debris, which Earth is now traveling through. This process is known as tidal disruption. It is the same mechanism that ripped comet Shoemaker-Levy 9 into pieces before its dramatic impact with Jupiter in 1994. When a celestial body approaches a deep gravitational well, the tidal forces can overwhelm its internal cohesion, causing it to disintegrate in a matter of seconds. Such a dramatic origin story is compelling, but does the evidence support it? If a tidal disruption event were responsible for the meteor stream, it would leave a very specific fingerprint in the sky. Astronomers would expect to find a tightly packed cluster of meteor orbits. This is because all the fragments would have begun their separate journeys from almost the same point in space and at the same time. Their orbital parameters would be nearly identical, with only minor variations introduced by the breakup itself. While these orbits would naturally spread out over eons, in the short term, they would form a sharp, concentrated grouping, not a diffuse and widely scattered stream. This is precisely the signature Schober went searching for. His paper contains a dedicated analysis, employing rigorous statistical methods on a large dataset to detect any sign of such a recent cataclysm. If a tidal disruption had occurred recently enough to explain the surge in fireballs, this analysis was designed to find it. But it found nothing. The outcome was a null result, complete with a quantitative upper limit. The contribution from any tidal disruption was calculated to be less than or equal to 2.3 times 10 to the power of -4. In simpler terms, this means that if tidal disruption is a factor at all, it accounts for less than 0.02% of the meteors. We observe a contribution so small, it is effectively zero. For all practical purposes, the data decisively rules out tidal disruption as the source of what Earth has been experiencing. This finding is profoundly significant. It dismantles the very foundation upon which many viral narratives are built, the assumption of a recent catastrophic event. These stories of an asteroid shattering or a cosmic collision creating a sudden debris cloud are dramatic and create a sense of urgency, but the data does not support them. In fact, the evidence points to the complete opposite scenario: the slow, patient process of a rock comet gradually disintegrating, a mechanism we have been exploring. We are left with two fundamentally different origin stories for the debris in Earth's path. One is a tale of slow thermal breakdown over millennia. The other is a story of sudden, violent fragmentation. One scenario implies an object that has been quietly shedding material for thousands of years, leaving a long, faint trail. The other suggests an object that came apart recently and violently. The evidence presented in Schober's paper points overwhelmingly toward the first, more ancient process. This suggests that the online narratives about a catastrophic breakup are, at best, misinformed and, at worst, deliberately sensationalized. The true importance of this lies in how it refines our understanding of what is actually happening above us. We now know with a high degree of confidence that the invisible object shaping our skies is not a freshly shattered remnant. Instead, it is a rock comet, behaving as rock comets do, on a timescale that predates all of human civilization. This is not a new event. It is an ancient one that our technology is only now beginning to perceive. And this brings us to a crucial point of perspective. The only mechanism that the data confirms is the slow, patient disintegration of a single, unseen rock comet. This means that hidden objects, operating on geological timescales, are actively shaping Earth's meteoroid environment in the present day, and we are only just starting to detect their subtle signatures. The parent body, therefore, is not an emergency, it is a revelation. And the revelation is not about a new danger, but about a gap in our own observational capabilities. This finally leads us to what Earth has actually been witnessing in its skies. The story of the object M2026A1 is one thread of this mystery. The story of the fireball anomaly is another. The question of whether these two threads are, in fact, the same is what we will explore next. We now turn to the 4.5 Sigma signal. For decades, the American Meteor Society has been meticulously documenting fireball activity. They gather eyewitness accounts, cross-reference them with instrumental data, track the recovery of physical meteorites, and curate one of the world's most comprehensive databases on events in Earth's upper atmosphere. For the most part, this dataset follows a predictable rhythm. Fireball counts rise and fall with well-known meteor showers like the Perseids, the Geminids, and the Leonids, before settling back to a baseline level. While occasional spikes can be tied to specific, isolated events, the numbers remain remarkably stable over long periods, with only minor deviations from the norm. However, in the first quarter of 2026, something changed. Beginning in March, the AMS started to log a significant rise in fireball reports. This was not a small uptick, but a substantial and statistically meaningful surge. By the end of the quarter, after careful analysis, the anomaly was classified at 4.5 sigma. For those unfamiliar with this statistical term, a 4.5 sigma event has a probability of occurring by random chance of only about 1 in 200,000. This was no fluke. This was a signal, a clear indication that something real was happening. So, what exactly was taking place? The data revealed several things occurring at once. The first clue was a doubling of activity from what is known as the anthelion source. The anthelion is a region of the sky centered on the point directly opposite the Sun from Earth's vantage point. Due to our planet's orbital motion, a significant amount of meteor activity naturally concentrates here. You can think of it as the headwind region of our orbit, the direction Earth is moving into as it travels around the Sunday. Meteors originating from the anthelion tend to be slower than average, as they are on orbits that Earth is catching up to rather than colliding with head-on. A doubling of activity from this specific source meant that whatever was feeding it was doing so at twice its normal rate. This was a critical piece of the puzzle. The second piece of the puzzle involved an uptick in fireballs at high declination. In astronomy, declination serves as the celestial equivalent of latitude on Earth. A high declination event, therefore, is one occurring in a region of the sky far from the celestial equator. A spike in these kinds of fireballs implies a source with a significantly inclined orbit, one that is tilted relative to the plane of our solar system. This is noteworthy because most known meteor streams follow paths with only modest inclinations. Such an anomaly could suggest a more tilted parent body, or perhaps contributions from several different sources. Then came the third, and arguably most astonishing, component. During the period of the anomaly, the American Meteor Society logged an incredible 1,693 long-duration sightings. These are not the fleeting flashes that constitute the majority of meteor activity. Rather, they are meteors that burn for an extended time as they traverse the sky. Such prolonged events are exceptionally rare, typically requiring a meteoroid of a specific size, composition, and entry angle. To see 1,693 of them in a single quarter was astounding, a figure 2.5 times the previous record. It was the kind of spectacle that draws people out of their homes to gaze at the heavens. Beyond what could be seen, there was also what could be heard: confirmations of sonic booms. A sonic boom occurs when a meteoroid is large enough and traveling fast enough to create a powerful shock wave by compressing the air ahead of it. These booms can be detected by sensitive infrasound networks, registered by seismometers, and sometimes even heard directly by people on the ground. The AMS was able to cross-reference its visual sightings with acoustic data, confirming multiple instances where both channels recorded the exact same event. This correlation is critical, as it helps to rule out simple reporting bias. If people were merely looking up more due to a viral trend, visual reports would increase, but the instrumental acoustic data would not. The fact that scientific instruments captured the same phenomena tells us that the events were undeniably real. And then, there were the meteorites. In a brief 9-day window, 2 confirmed HED meteorites, which stands for howardite, eucrite, and diogenite, were recovered. This specific class of stony meteorite is believed to originate from the asteroid Vesta. Finding 2 of them in such a short span of time is highly unusual in any circumstance. The physical recovery of a meteorite provides the ultimate confirmation that something extraordinary is taking place. You cannot simply report a meteorite into existence. Either the rock is physically present, or it is not, and in this case, 2 of them were. Of course, skeptics of the anomaly offered a ready explanation. They noted that 2026 had witnessed a significant increase in AI-generated content and the social media amplification of celestial events. Perhaps, they argued, the anomaly was not a reflection of increased activity in the sky, but rather an artifact of modern attention spans, amplified by algorithms. It is a reasonable hypothesis, and if the only data that had changed were visual reports, it would warrant serious consideration. But the visual reports were not the only thing that changed. The acoustic data changed, the seismic data changed, the infrasound detections changed. And most crucially, physical rocks fell from the sky. One cannot generate an HED meteorite with a clever algorithm, nor can a viral video produce a sonic boom. The consistency across these multiple, independent channels, the fact that visual, acoustic, and physical recovery data all pointed in the same direction, rendered the explanation of reporting bias inadequate. Something was truly happening in the near-Earth environment. More material than usual was entering our atmosphere, some of it large enough to make noise, and some of it even reaching the ground. This pattern could not be explained by any of the known meteor showers active during that time. And this is where the story begins to circle back to the hidden parent of VET 2026A1. If there was indeed an unidentified source of additional material in Earth's orbital path, and a peer-reviewed paper had just identified a new meteor stream from an unseen parent in that exact window, one must ask a critical question: could these 2 phenomena be the same thing? Not merely 2 separate events coincidentally happening at once, but rather a single underlying system becoming visible from 2 different perspectives simultaneously. This is precisely what you might expect if you were watching an unseen object finally reveal itself through its effects. The AMS anomaly represents the first half of the evidence, and Shower's paper represents the second. The question of whether they align, whether the timing and geometry truly match, is where this story either resolves into a coherent picture or fractures into a handful of unrelated observations. That is what we will explore next. This is the point where the narrative either solidifies or falls apart. If Shower's M22601 stream and the AMS fireball anomaly are truly connected, then the evidence for that link must appear in the timeline, the geometry, and the physical characteristics of the observed meteors. Let us walk through each of these elements. First, the timeline. Shower's analysis pinpointed the active window for the M2026A1 stream as running from approximately March 16th to April 7th. This 3-week period is typical for meteor streams associated with near-Earth objects, representing the time it takes for Earth to pass through the debris trail. Meanwhile, the AMS anomaly reached its peak in late March and carried on into early April. When you overlay these two windows, they are not just close, they are nearly identical. The overlap spans about 3 weeks, meaning the period when Earth was traversing the M2026A1 stream is essentially the same period during which the fireball anomaly was at its most intense. While this alignment on its own is suspicious, it is not yet conclusive. Two events happening in the same window could still be a coincidence. To move beyond mere coincidence, we must examine the geometry. Here too, the pieces align. The radiant of the M226A1 stream, the point in the sky from which the meteors appear to originate, is located within the region where anthelion source activity is concentrated. The anthelion is the part of the sky roughly opposite the Sun, in the direction of Earth's orbital motion. Meteor streams whose parent bodies have specific orbital paths often produce meteors that radiate from this region. The geometry of M2026A1 places its radiant squarely in this general area, which perfectly matches the doubling of anthelion activity that the AMS had logged. We now have two independent observations, pointing not just to the same time, but to the same part of the sky. This is far more than a coincidence. It appears to be a direct match. The physical characteristics of the meteors also align with this conclusion. The particles associated with the M2026A1 stream possess a composition consistent with moderately fragile meteoroids. They are not the ultra-dense metal-rich fragments of an asteroid, nor are they the light, ice-dominated grains of a typical comet. Instead, they occupy a middle ground, characteristic of material shed from a rock comet that has been repeatedly heated and stressed during its close passes to the Sunday. It is this specific type of material that, upon entering Earth's atmosphere, tends to create bright, slow-moving fireballs. They are bright because they carry enough mass to generate substantial light, and slow because their orbital velocity is similar to Earth's, meaning they do not impact the atmosphere at the hypersonic speeds of higher energy meteors. And this is where the theory meets the observed reality in a compelling way. The signature of a bright and slow fireball is precisely what the American Meteor Society was reporting in increased numbers during the anomaly window. The long-duration sightings, those remarkable enough to draw people outdoors, were disproportionately this kind of event. The physical signature of the incoming objects perfectly matches what the M2026A1 stream would be expected to produce. When all these pieces of evidence are assembled, they form the first plausible physical explanation for the anomaly that the AMS had been tracking since March. The stream's origin, its radiant point in the sky, the timing of its arrival, and the physical properties of its meteors all converge. This is not mere speculation. It is a confirmed meteor stream, identified in a peer-reviewed paper, whose characteristics align with an anomalous event that had remained unexplained for nearly a month. However, it is crucial to approach this alignment with the caution that defines rigorous science. The scientific community is rightly wary of claims of causation, because even a strong correlation does not definitively prove a direct link. Just because two phenomena line up in time, space, and physical signature does not mean one is the absolute cause of the other. It is entirely possible that M2026A1 contributed to the anomaly without being its solitary source. We could be looking at a scenario where multiple sources were active simultaneously, with this newly identified stream being just one component among several. In fact, there are compelling reasons to believe this is precisely what was happening. The falls of HED meteorites during the anomaly window, for instance, do not fit the M2026A1 profile. These meteorites originate from Vesta, a major asteroid in the main belt, not from a sun-grazing rock comet. Therefore, the two head meteorite falls recorded during this period are almost certainly unrelated to the meteor stream. They represent a separate signal, perhaps nothing more than a statistical fluctuation in the background rate of meteorite falls, or perhaps an indicator of something else entirely. This discrepancy suggests we are observing more than one phenomenon at play. The mystery deepens when we consider the fireballs observed at high celestial declinations. The M2026A1 stream can only partially account for these events. While some of them could have originated from the stream, depending on their precise entry point into the atmosphere, the high inclination portion of the anomaly seems to require contributions from other sources. This points to the possibility that we may need to look for other, as yet unidentified streams to complete the picture. What emerges from this analysis is a partial, yet profound explanation. The M2026A1 stream accounts for a significant portion of the events logged by the AMS, but it does not account for all of them. And it is within this very gap, the space between what the stream can explain and the full scope of the anomaly, that some of the most compelling questions arise. One framework for understanding this complexity is the idea of a compound anomaly. This hypothesis suggests that what we are observing is not a single, isolated phenomenon, but rather multiple, separate events that are overlapping in time. Their combined signal creates the illusion of one large event, when in reality it is several. This is a more challenging hypothesis to test, and certainly more difficult to communicate, as it requires holding multiple partial explanations in mind at once. But it may offer the most truthful depiction of what is unfolding in our skies. When we examine the likelihood of these independent events aligning purely by chance, the odds become remarkably slim. The probability of an unrelated meteor stream being discovered in the exact window of an unexplained fireball surge with matching geometry and physical signatures is very low. The chance of that occurring at the same time that two unrelated asteroids make close passes to Earth within 24 hours, all converging within a single week, is even lower. This is not to suggest a grand, predetermined cosmic design. Instead, it hints that something about Earth's current orbital environment is simultaneously producing multiple, noticeable signals. Scientific prudence demands that we avoid overstating our conclusions. We do not have confirmed causation. What we have is a strong correlation, a partial explanation, and a framework where a peer-reviewed discovery matches a significant, but not complete, portion of what an independent dataset recorded. This marks a critical turning point. For weeks, the AMS anomaly was simply a mystery. Now, for the first time, a physical mechanism exists that can at least partially account for it, a mechanism validated by peer review just 5 days ago. This is the essential development to grasp. Theory and observation have finally met. The calculated stream proposed by Damir Shegon, derived from orbital mechanics and meteor clustering, aligns with what the AMS was witnessing through its ground-based cameras and network of observers. This is the very essence of scientific discovery, the moment when a mathematical model and real-world data begin to describe the same reality. And if this is only one component of a larger system, if the compound anomaly hypothesis is correct, then what we are witnessing is the first signal of a near-Earth environment that contains more unseen sources than we currently understand. This aligns perfectly with the central narrative we have been exploring on Calm Space. The hidden is becoming visible through its effects, and those effects are proving to be more complex and numerous than we ever imagined. Let us now consider several additional data points that, while not decisive on their own, contribute to the broader picture of what has been happening in Earth's orbital neighborhood. These signals are independent of both the AMS fireball data and the M2026A1 stream paper, which is what makes them so interesting. In science, the power of independent verification cannot be overstated. When multiple, unrelated observational channels begin to point in the same general direction, the signal must be taken seriously, even if each channel is individually noisy. A single dataset, no matter how robust, can always be flawed for reasons no one has yet considered. But when two or more datasets, gathered using different instruments and methods, point toward a similar conclusion, they become far more difficult to dismiss. Independence provides leverage. A single data point can be dismissed as a coincidence, but when 3 or 4 independent signals emerge, they become nearly impossible to ignore. This principle guides our evaluation of what is truly happening in the near-Earth environment. We don't simply look for one channel to light up. We search for multiple channels that activate simultaneously, and at this moment, they are. The first signal originated from the Moon. During a dedicated observation window for the Artemis II mission, lunar observers documented 6 distinct impact flashes on the Moon's surface. These events occur when meteoroids, unhindered by any atmosphere, strike the lunar regolith. Their immense kinetic energy is instantly converted into brief, brilliant bursts of light. While these flashes last for only a fraction of a second, they are perfectly detectable with the right instruments. The resulting data is among the cleanest available for understanding our cosmic neighborhood. There is no atmospheric distortion to account for, no eyewitness subjectivity to filter out, and no delay in reporting. A meteoroid strikes, light is emitted, and a camera records it, a simple chain of physics and observation that leads to a straightforward conclusion. To see 6 impacts during a focused observation period is a higher rate than baseline models would predict. While not a statistical impossibility, it sits at the upper end of expectations, a detail that gains significance when viewed alongside other events. The Moon, of course, occupies the same orbital vicinity as our own planet. This may seem like an obvious fact, but its implications are profound. Orbiting at an average distance of about 239,000 miles, the Moon and Earth are, on a cosmic scale, essentially in the same place at the same time. They share an orbital environment, sweeping through identical regions of space as our two-body system journeys around the Sunday. This means that if Earth is passing through a stream of debris, the Moon is almost certainly doing so as well. The geometry isn't always perfect. The Moon's position in its orbit can place it inside or outside the densest part of a debris trail. But broadly speaking, what influences Earth also influences the Moon. An increase in lunar impact flashes during the same period as Earth's fireball anomaly is therefore highly suggestive. It provides confirmation that is entirely independent of Earth-based reporting, meaning it cannot be explained away by factors like AI-driven reporting, inflation, or social media excitement. It is simply a record of flashes on the Moon captured by professional instruments that have no headlines to chase. However, the universe rarely presents such a neat and tidy picture. The spatial correlation between these lunar flashes and the M2026, a one stream, is not perfect. Some of the impact geometry on the Moon does not precisely match the stream's radiant, the point in the sky from which the meteoroids would appear to originate. When their paths are projected backward, they don't all fall cleanly within the region where the M2026, a one stream, should be leaving material. Furthermore, the Moon's location relative to Earth during the observations means that not all impacts can be directly linked to the stream. Some could be from the stream, while others may be from unrelated background sources. Without more detailed analysis of their trajectories, we cannot definitively separate them. Yet, the general timing and the elevated rate still contribute to a broader image of an unusually active period. Seeing 6 impacts was unexpected. Something was clearly happening. And this signal comes from a channel completely free of the reporting biases that can complicate Earth-based data. A second, independent signal comes with an important caveat, serving more as a lesson in data interpretation than a direct confirmation. It concerns the well-known challenges with fireball data from CNEOS, the Center for Near-Earth Object Studies. CNEOS maintains a public database of fireball events detected by sensitive government sensors that cover most of the globe. This database is an invaluable resource for researchers studying fireball activity, but it possesses known limitations, most notably in its coordinate accuracy. The sensors were not originally designed for this purpose, and the conversion of raw detection data into precise fireball coordinates relies on assumptions that are not always reliable. A case in point occurred on March 25th, when CNEOS listed coordinates for an event that were off by approximately 1,800 meters from the actual location, as determined by cross-referencing with American Meteor Society eyewitness reports and local news. While that distance might not seem vast, for scientists trying to trace an object's origin or match it with other instrumental data, such a discrepancy is significant enough to send an investigation chasing a phantom. This type of error is not intentional. It is a widely understood limitation of the system and its data processing, but it underscores a critical point. Any single detection from the CNEOS database must be independently verified before it can be trusted as solid evidence. This necessity for verification means that you cannot simply take a number from the database and treat it as fact. It must be checked against data from the AMS, other NASA datasets, local reports, and any other available instrumental confirmations. Only when all the numbers align can the event be considered trustworthy. If they don't, the meticulous work of figuring out which data source is incorrect begins. This process requires time and expert judgment, which is why the public-facing narrative often lags behind the true state of the data. The first report of a fireball is almost always provisional. The confirmed version may not be released for days or even weeks after all the cross-verification is complete. During the anomaly window, a great deal of the work performed by independent researchers was precisely this kind of careful verification. It involved pulling events from the CNEOS database, checking them against AMS reports, searching for news coverage of ground-level sightings, and examining local infrasound data where available. Through this painstaking process, they began to build a consolidated, more reliable picture of what was actually happening in the skies above. It is in this meticulous work that the real story begins to take shape, far from the initial unverified reports. While some events were confirmed with relative speed, others demanded a deep dive into regional news archives across multiple languages just to find corroboration. In this painstaking process, a few reported events were found to be errors and were quietly discarded. Others proved to be both real and significant, yet their characteristics differed from what the initial data suggested. This verification is a slow and imperfect endeavor, the kind of meticulous work that rarely makes headlines because it lacks sensationalism. But it is precisely this work that distinguishes a plausible narrative from a verified one. It also means that our current grasp of the anomaly is in a constant state of refinement, as new information arrives and old data is corrected. This journey through the data reveals a fundamental limitation: uncertainty. We do not possess a perfectly clear image of everything that occurred in Earth's atmosphere during March and early April. Anyone claiming otherwise is either working with non-public information or is overstating their confidence. Instead, what we have is a composite picture, assembled from numerous, partially reliable sources that have been cross-referenced as thoroughly as possible. This picture is strong enough to support the conclusion that something unusual took place, but it is not yet detailed enough to pin down every single aspect. This can be an uncomfortable position, as we are naturally drawn to stories with clean resolutions and exact figures. We prefer to state precisely what happened, when, and why. Science, however, does not always provide such immediate clarity. especially in the initial weeks after a new phenomenon is observed. The precision arrives later. Only after the data has been cleaned, verified, reprocessed, and compared across multiple independent channels. What we possess right now is merely the first draft of this story. The final version will be more defensible, and it will likely look somewhat different from what we see today. Here is the point that deserves emphasis. Even with imperfect data, coordinate errors, and the need for exhaustive cross-verification, the overall signal remains consistent. It points toward an active and partially unseen meteoroid environment. This is not a conclusion that hinges on any single data point being flawless. Rather, it is a conclusion that emerges from the convergence of multiple lines of evidence, each with its own flaws, yet all pointing in the same general direction. The lunar flashes indicated elevated activity. The visual reports from the American Meteor Society also suggested elevated activity. Acoustic confirmations provided another layer of evidence, as did the recovery of meteorites. While no single one of these is decisive, their combined weight paints a picture that is difficult to explain away with any simple, trivial cause. Something happened. In some form, something is still happening. The lingering questions are what, why, and just how much of it we can actually map. The hidden parent of the M2026A1 meteor stream is not the only unseen contributor to our cosmic neighborhood. It is simply the first one we have managed to identify. This is a concept worth pausing on, for it reframes everything we have just witnessed. We did not simply discover a unique, one-of-a-kind object. What we discovered, with high confidence, is that at least one such object exists within the sunward blind zone, actively feeding a confirmed meteor stream into our planet's orbital path. And if one exists, statistical reasoning strongly suggests that others do too. The complex nature of the anomaly implies that there are likely other sources still waiting to be found. The very observational gaps that rendered the hidden parent invisible are the same gaps that might be concealing additional sources right now, tonight, as you are watching this. That blind zone did not vanish when Schober's paper was published. It is still there. It is still a blind zone. And it is still catching parent bodies we have not yet seen. This is precisely why the next chapter of this story is so important. Because while scientists have been methodically working through the data, building models, cross-verifying sources, and publishing peer-reviewed papers, the internet has been moving at a much faster speed. The story it has been telling does not always align with the story told by the data. The scientific process is deliberate and cautious. The viral process, by contrast, is explosive and immediate. One takes months to get something right. The other takes mere minutes to get something mostly wrong. It is in the gap between the viral narrative and the scientific reality that much of the public's confusion resides. That gap is worth examining, as it tells us something vital about how we collectively make sense of discoveries like this one, and about how the true shape of a story can become distorted when it leaves the scientific journal and enters the social media feed. Part 10. The viral narrative versus scientific reality. If you scroll through any social media platform right now, you can find versions of this story that sound dramatically different from what we have been discussing. The viral framing typically unfolds like this. Earth is flying through a dangerous cloud of asteroid debris. The recent fireballs are just the beginning. A hidden object is breaking apart. Something is coming. The government is not telling us the whole story. The skies are about to get worse. You have seen the posts and the videos. If you have opened any major platform in the last 24 hours, you have probably encountered at least one. The thumbnails are aggressive, the captions are dramatic, and the comment sections are filled with people asking if they should be preparing for disaster, stocking up on supplies, or looking at the sky with a new sense of fear. Some of this narrative is loosely anchored in real events, which is what makes it so powerful. It is true that we are passing through the debris trail of an object that was previously unseen. It is also true that fireball activity has been genuinely elevated, and there is a peer-reviewed paper confirming the existence of a new meteor stream. These facts, on their own, provide the seed material from which viral narratives grow. This is an important point to acknowledge, because if the underlying story were completely false, it would be much easier to dismiss the sensationalized versions. The problem is that the underlying story is real. It has simply been reshaped as it traveled, transformed into something that carries a far different weight than the original version did. What occurs in the space between the facts and the narrative is a kind of digital compression. In this process, the timeline gets crushed, the scale gets amplified, and the tone shifts from one of careful observation to one of urgent warning. And once that compression has taken place, it is incredibly difficult to reverse. You cannot easily reintroduce nuance into a story that has already been flattened for the algorithm. Of all these distortions, the compression of timescales is perhaps the biggest source of misunderstanding. To truly grasp the nature of astronomical events, it is sometimes necessary to pause and adjust our perspective. When we hear that Earth is passing through a debris trail, the image that comes to mind can be misleading. What is actually occurring is that our planet's orbit is intersecting a vast region of space where dust and minuscule particles have been accumulating for millennia, perhaps even tens of thousands of years. The unseen parent body of the object, known as M2026 A1, has been shedding this material for a period far longer than recorded human history. The stream we are now crossing is the grand sum of all that ancient, gradual leakage, concentrated along a specific path through the solar system. This intersection is not a brief event. It can last for weeks. During this time, the density of matter increases by only a minuscule amount above the near-perfect vacuum of interplanetary space. To put this into perspective, if you could somehow collect all the particles from a cubic kilometer of space within the densest part of this stream, you would be left with what amounts to a handful of sand scattered across a volume the size of a small city. This is the subtle reality we are observing. It is not a cloud or a wall of rock, but a faint statistical whisper in the vast silence of space. This distinction between perception and reality is critical. The particles themselves are mostly no larger than grains of sand. While some may be bigger, they are overwhelmingly too small to cause any harm beyond creating a bright, fleeting streak across the night sky. This means that our homes, our vehicles, our satellites in orbit, and even the International Space Station are all perfectly safe. The stream poses no significant physical threat to any of our infrastructure. The popular image of Earth plowing through a dense cloud implies a level of danger that might warrant concern, something that would be newsworthy for reasons beyond scientific curiosity. The truth is far more serene, a diffuse, largely invisible phenomenon whose primary effect is a slight, statistically measurable rise in fireball activity. This is something the automated cameras of the AMS can detect. But an individual observer looking up at the sky might not notice any difference from one night to the next. If you had gone stargazing last week, you would have seen the same familiar celestial tapestry, perhaps with a few extra bright meteors if you were fortunate. You would not have seen a cloud because no such cloud existed. Here, the profound difference between geological and human timescales comes into sharp focus, a concept that often challenges our intuition. The human mind evolved to perceive the world on a scale of days, weeks, and years. Our news cycles operate in hours, and our attention is often captured for mere seconds. But the universe operates on grander timelines. Orbital mechanics unfolds over thousands of years, while geology plays out over millions. When we attempt to compress these immense geological timescales into the brief window of a human news story, the result can feel distorted and unnatural to those who study these processes. The kind of slow, thermal disintegration that produces the debris from M2026, A1's parent, is a geological phenomenon. The stream we are passing through is not a new or sudden event. It is the collected history of a process that began long before our species even learned to use language. The debris was already there when the pyramids were built and when the last ice age receded. And yet, when it appears in a headline, it is presented as if it all began last month. Framing this ancient, gradual process as something sudden and urgent fundamentally misrepresents the timeline. It takes a slow, patient, and majestic cosmic phenomenon and squeezes it into a headline designed to feel immediate and alarming. This very act of temporal compression is what creates the anxiety. It is also what makes the viral version of this story feel so profoundly different from the scientific one. The underlying physics has not changed. The astronomical observations have not changed. The actual material in the stream has not changed. The only thing that has changed is the narrative frame placed around the information. And it is this frame that does nearly all of the emotional work. Part of the reason this happens lies in the fundamental conflict between scientific communication and the mechanics of online media. Science, by its very nature, is a slow and meticulous process. It is cautious, and it qualifies its findings at every turn. A well-written scientific statement is filled with careful language, acknowledging uncertainty and clearly defining the limits of its conclusions. Reading a planetary science paper, you will find words like probable, possible, consistent with, and suggestive of. Scientists communicate this way because their profession demands it. Overreaching can damage a career, and claims that are later disproven become cautionary tales. The incentives within the scientific community overwhelmingly favor restraint. In stark contrast, social media platforms reward clarity, urgency, and a strong emotional hook. The structure of the attention economy creates this dynamic. Consider how this plays out. A phrase like, "Earth is passing through a debris stream produced by a slow thermal disintegration process over a geological timescale," will not perform well on any algorithm. It is precise, but it lacks the punch needed for widespread sharing, commenting, or viral video adaptations. On the other hand, the phrase, "Earth is flying through an asteroid cloud," performs exceptionally well. While both statements may be rooted in the same physical situation, they communicate vastly different realities. The platforms we use will invariably amplify the second version over the first, not out of any malicious intent, but because that is how the attention economy processes information. Urgency triumphs, while nuance is often left behind. This is the environment in which we all receive our information, and it helps explain why the viral version of nearly every science story tends to drift away from the scientific original over time. It is important to recognize a subtle overlap between truth and exaggeration that makes this issue particularly complex. The viral narratives are not entirely fabricated, and to dismiss them as pure misinformation would itself be an inaccurate framing. They are compressed and sensationalized, but they are grounded in real events. The meteor stream is real. The documented anomaly in fireball activity is real. The detection of a hidden parent object through its subtle effects is a genuine and exciting scientific first. The problem is not that the viral version is pure fiction. The problem is that it combines true data with an inaccurate narrative frame. And it is that frame that ultimately changes the meaning of the information, transforming a story of subtle cosmic discovery into one of unfounded alarm. The difficulty in refuting certain claims arises when they are built around a core of truth. It becomes a challenge to push back on a specific point when the response can be, "But the asteroid is real," or "the fireballs were documented." And while those individual statements are correct, the issue is not with the facts themselves, but with the emotional framework constructed around them. The language we choose is of critical importance in communicating complex realities. and it's worth exploring what this difference looks like in practice. For instance, stating that Earth is passing through a debris stream is a precise and accurate description. To say, however, that Earth is flying through a cloud of asteroid debris implies a level of density and danger that is not supported by the evidence. Similarly, noting that a hidden asteroid has been detected via its meteor stream is a statement of fact. Claiming an invisible asteroid is attacking Earth is a departure into fiction. We can report that fireball activity has been elevated, but it is an exaggeration to say the skies are erupting. It is correct that we are moving through material that has accumulated over millennia. It is incorrect to suggest something is actively breaking apart right now. These subtle shifts in wording can create vastly different perceptions of the same event. This is why careful scientists and writers deliberate so intensely over specific phrases. It is a recognition that language is the bridge between reality and our perception of it. This brings us to the more extreme interpretations that often surface during these discussions, ideas you are likely to encounter regardless. It is better to address them with context than to let them be found without it. Theories involving Nibiru or Nemesis, which propose a hidden, planet-sized object on an eccentric orbit that periodically endangers Earth, have been in circulation for decades, long before this current story. They have been attached to nearly every significant astronomical event of the last 20 years, from planetary alignments to solar cycles. And yet, they simply do not apply here, because the fundamental physics does not support them. A body of that immense size would exert a powerful gravitational influence on the entire solar system, perturbing the orbits of the outer planets in ways that would be impossible to miss. It would be evident in long-term astronomical records and gravitational models. The fact that it appears in none of these records is not for a lack of looking. It is strong evidence of its absence. If such an object existed, we would know, not because of a government disclosure, but because the fundamental mathematics of the solar system would fail to add up. And as it stands, the math closes perfectly. The hidden parent of the 2026 A1 stream is not a planet. It is an asteroid, likely small, rocky, and comparable in size to other known near-Earth objects. It is hidden only in the sense that it occupies our observational blind spot, not because it is supernaturally undetectable. When the NEO Surveyor mission launches and provides infrared coverage of the region near the Sun, this object will almost certainly be one of the first it finds. We will get an image, calculate an orbit, and likely obtain a spectrum. The mystery, as it is a consequence of our current instrumentation, not a fundamental truth about the object's observability. This is not a conspiracy. It is a capability gap, and one that is already being addressed by a mission well into its development. The viral narratives that have taken hold arise from this very intersection of real but incomplete information about unseen objects. The data is real, the gap in our knowledge is real, and the story itself is real. But when this information enters the public sphere without the scientific context needed to properly interpret it, it becomes compressed into something that feels far more dramatic than the underlying reality. This is not a failure on anyone's part, but an almost inevitable outcome when a genuinely strange discovery travels from a peer-reviewed journal to a social media comment section. The information must change its shape to survive that journey, and in doing so, it sheds some of the accuracy that made it valuable in the first place. The scientific reality, however, is stranger and, in its own way, more fascinating than the viral version. We have, in fact, confirmed the existence of an asteroid through its effects alone, a remarkable feat. We have identified what may be a new class of active near-Earth object. We have documented an unprecedented fireball anomaly with confirmation from multiple channels. These facts, when told with care, are more than sufficient to mark this as a legitimately historic moment in observational astronomy. The story does not need to be inflated to be remarkable. It already is. It simply needs to be told honestly. And the honest version, as we have been exploring, is about a blind spot in our vision of the sky. It is a story about a population of objects that lives inside that blind spot, and the first clear signal that population has finally sent us to announce its presence. That is the actual story. The viral version is loud and simple. The real version is quieter, weirder, and ultimately far more interesting once you sit with it long enough to feel its true shape. To be honest about the current situation, it is crucial to acknowledge that as of this moment, scientists do not have a single, unified answer for what is happening. There are several ways to interpret the convergence of recent events, and each interpretation has evidence both for and against it. Let us walk through 4 of them. The first interpretation is simply coincidence. In this view, the 2 asteroid flybys, the publication of the meteor stream paper, the documented fireball anomaly, and the observed lunar impact flashes are all separate, unrelated events. They just happen to occur within roughly the same period, a product of random alignment and statistical chance. The human mind is an extraordinary pattern-finding machine, wired to connect dots even in a sea of noise. This brings us to our first interpretation, coincidence. From this perspective, the various astronomical events are simply that unrelated occurrences happening in close succession. The evidence for this is compelling in some respects. For example, the 2 asteroid flybys are confirmed to be entirely separate from the meteor stream. Analysis of their trajectories shows no connection to the stream's geometry, and they are not fragments from some hidden parent body. They are genuinely independent celestial passers-by. While having 2 such close approaches within a single 2-4-hour period is certainly noteworthy, planetary defense surveys log sublunar flybys with regularity, making such a cluster statistically unlikely but not impossible. The fireball anomaly, at a 4.5 sigma level of significance, is harder to brush aside. That is the very definition of a signal, not a random fluctuation. Still, one could argue that while the meteor stream and the fireball surge are both real, their apparent connection is an illusion of timing and perspective. Under the most rigorous standards of proof, coincidence remains a technical possibility. Its greatest weakness, however, is the sheer number of independent events one must accept. A new stream, a surge in fireballs, 2 asteroid flybys, and a series of lunar impacts all occurring in the same narrow window begins to strain credulity, even if it remains mathematically possible. A second, more balanced interpretation is that of a partial explanation. This view, grounded in scientific conservatism, is likely where most planetary scientists would currently stand. It posits that the meteor stream, M2026A1, is indeed real and is actively feeding debris into Earth's path. This stream is responsible for a significant portion of the observed fireball anomaly, specifically the events that align with the stream's radiant, timing, and meteoroid characteristics. However, this hypothesis is careful not to overreach. It acknowledges that the stream does not account for everything that was witnessed. The unusual HED meteorite falls, the surge in high declination fireballs, and perhaps even the lunar impact flashes appear to have separate origins, not connected to M2026A1. The strength of this approach lies in its discipline. It accepts strong evidence, explains what can be explained, and openly acknowledges that other factors are at play. It leaves the door open for future observations to complete the picture. Its only real weakness is that it feels incomplete. We are drawn to narratives with clear beginnings and endings, and a partial explanation offers a progress report instead of a final resolution, telling us what we know, what we don't, and what remains to be discovered. The third possibility is the most speculative, yet also the most intriguing. the broad environmental shift hypothesis. This framework suggests we are not observing isolated events, but rather a collection of symptoms pointing to a larger, more fundamental change in Earth's local meteoroid environment. It's a perspective that considers the convergence of multiple, independent signals: the stream, the fireballs, the lunar impacts, an elevated rate of meteorite recoveries, and two previously unknown asteroids passing by in a single day. Taken individually, each of these events falls within the realm of normal variability. But when they occur collectively, they begin to form a compelling pattern. If this pattern is real, it raises a profound question. Is the space around our planet currently more active than our baseline models predict? This could be happening because several sources are contributing debris simultaneously, or because Earth has entered a region of higher overall meteoroid density for reasons not yet understood. This remains a speculative idea, one that cannot be easily tested with current data. Our observational capabilities are not yet sufficient to distinguish a genuine environmental shift from a temporary, though significant, statistical spike. The ultimate test for this hypothesis lies in the future. If the second quarter of 2026 shows continued elevated activity, the idea of a shift gains strength. If activity drops back to baseline, the hypothesis will weaken. Finally, we arrive at the fourth interpretation, the null hypothesis, which proposes that nothing unusual is happening at all. This viewpoint argues that everything we are observing falls within normal variability, but our perception is skewed by vastly improved detection technology and the amplifying effect of social media. The fireball anomaly, in this light, is not a true surge in events, but an illusion created by more cameras, more automated reporting, and more efficient networks. What would have been an unremarked quarter in the past now appears as a dramatic spike. The meteor stream is considered real, but minor, its contribution to our environment negligible. The asteroid flybys are routine, and the lunar impacts are within baseline rates. The strength of the null hypothesis is its simplicity. It requires no new physics or hidden cosmic processes, only the acknowledgement that our ability to see what was always there has improved dramatically. Historical underreporting is a well-known phenomenon. The American Meteor Society itself notes that its data from 2 decades ago is not comparable to current data due to network expansion. Its weakness, however, lies with the physical evidence. You can explain away visual report inflation, but you cannot explain away the head meteorite falls as a detection artifact. Those rocks are either on the ground or they are not. And the appearance of 2 in just 9 days is a tangible data point that this hypothesis struggles to dismiss. In evaluating these 4 distinct interpretations, the evidence currently points most strongly toward a partial explanation. It best accommodates the complex and sometimes contradictory data without resorting to either extreme coincidence or unproven speculation. The coincidence hypothesis is becoming increasingly difficult to defend as more signals accumulate. The broader environmental shift hypothesis remains a fascinating possibility for the future, but it is not yet testable with the necessary scientific rigor. And while the null hypothesis correctly identifies the impact of modern technology on our observations, it ultimately fails to account for all the physical evidence. The path forward, it seems, is to build upon the solid foundation of what is known, while continuing to investigate the many questions that remain. The most elegant explanation is often the one that accounts for the most data with the fewest assumptions. However, it is crucial to emphasize that in this case, we lack decisive evidence for any single interpretation. The current state of our knowledge is one of genuine uncertainty. This is one of those classic moments in science where the question is far newer than the answer, and arriving at that answer will require more data, more time, and more meticulous work. The scientific method truly shines in these moments. patiently gathering evidence to navigate a landscape of open questions. Upcoming observations will be critical. Data from AMSQ2 will be particularly important. If the fireball anomaly extends into the second quarter, it would lend weight to the hypothesis of a broader environmental shift or a more complex compound anomaly. Conversely, if fireball activity returns to its baseline, the anomaly would appear to be a more localized event, perhaps tied specifically to the M2026A1 meteor streams window. Furthermore, should global networks discover additional meteor streams in the coming months, it would suggest more hidden parent bodies and support the broader shift theory. Ultimately, NASA's NEO surveyor, once operational, will serve as the final arbiter on the question of the sunward blind zone. If it reveals a population of rock comets consistent with modeling predictions, it will confirm the blind zone is populated and validate the inference-based detection methods used. If that population proves smaller than expected, the entire picture would change significantly. The scientific process here will not be swift. It is a journey that will play out over many years. We are at the very beginning of this inquiry, not the end. The answer will not emerge from a single observation or one groundbreaking paper, but from the slow, careful accumulation of data, the rigorous testing of competing hypotheses, and the gradual refinement of our understanding. What is new and significant about this particular moment is that we now have, for the very first time, a testable hypothesis that connects a peer-reviewed discovery to an observational anomaly. This is the milestone. The breakthrough is not that we know the answer, but that the question has finally been framed with enough precision that it can, in time, be answered. Let us now bring all these threads together, because the complete picture is quite different from the headlines that have circulated. When we step back, a more profound and interconnected story begins to emerge. The convergence of events is what makes this moment so remarkable. We witnessed two distinct asteroid flybys within a 2-4-hour period, one of the closest back-to-back pairings logged in recent memory. This coincided with the publication of a peer-reviewed paper identifying a previously unknown meteor stream, one whose parent body has never been directly seen. All of this unfolded against the backdrop of a 4-5 Sigma fireball anomaly that had been building since March, its cause a mystery until just days ago. And woven through it all was a viral narrative that raced ahead of the science, compressing geological timescales into urgent warnings that the actual data did not support. Individually, none of these components would be considered earth-shattering. Asteroid flybys occur, scientific papers are published, fireball counts fluctuate, and viral narratives often form around major space news. The true significance lies not in any single event, but in their collective meaning. What makes this moment different is that when you assemble all the pieces, they form a coherent story about the limits of detection, a story about what we can see, what we cannot, and how much of the world around us operates in regions we have not yet learned how to observe. The central discovery here, the one that must not get lost in the noise, is the invisible parent asteroid. The two visible asteroids that skimmed past Earth were merely the trigger for public attention, not the main story. They are what put this sequence of events into the news cycle and made people take notice. But the actual substance, the discovery that will be remembered long after this week has passed, is the unseen third body. This object, lost in the sun's glare, has never been directly observed. Its very existence is known to us only because its debris has been burning up as meteors in our atmosphere. Viewing the flybys through this lens fundamentally changes their meaning. They become a kind of cosmic coincidence that drew public attention to a moment that was already scientifically significant for entirely separate reasons. The flybys, then, were not the story. They were the spotlight that illuminated the story. And under that spotlight, we can now clearly see a detection gap so fundamental to our methods that it has been hiding an entire category of active near-Earth objects for an unknown length of time. This raises the profound question of what else might be concealed from our view. This detection gap is the core issue, and its implications are far larger than any single object. If we have now confirmed through inference that at least one rock comet, M2026A1, exists in the sunward blind zone, producing a significant meteor stream and affecting Earth's upper atmosphere, how many more could there be? Mathematical modeling, based on what we know about the orbital distribution of near-Earth objects, suggests the answer is likely many, possibly dozens, or even hundreds. The blind zone is not a small region of space, and the objects that orbit within it are precisely the kind that leave behind debris trails. We are, in essence, reconstructing a population we cannot directly observe. Every identified stream, every anomaly traced to an unseen parent, becomes another data point in that reconstruction. M2026A1 is the first confirmed case, but it will almost certainly not be the last. This realization forces a re-evaluation of our planetary defense strategies. Our approach is built on two core assumptions. First, that we can identify dangerous objects early enough to characterize them, and second, that our catalogues are comprehensive enough to have already accounted for most of the larger threats. The sunward blind zone challenges both of these foundational beliefs. By definition, objects in that zone are invisible to our current instruments. They can remain on Earth-crossing orbits for decades without ever being detected, and while most of them are probably small enough not to pose a significant impact threat, we simply do not know for sure because we cannot see them. It is important, however, to contextualize the nature of this potential hazard. The slow disintegration of rock comets means they do not represent a sudden, catastrophic threat. These bodies do not spontaneously fall apart and create an impact hazard out of nowhere. Instead, they shed material gradually through a process that unfolds over timescales that dwarf human experience. This makes them a persistent, long-term feature of our solar system. A subtle and ongoing process rather than an immediate and acute danger. Understanding this helps place the nature of this risk into its proper perspective. The inability to see these objects means that characterizing them individually, predicting their movements, or assessing potential hazards remains impossible. We are faced with an observational gap that we must close. While future missions like NEO Surveyor will certainly help, for now, we are effectively flying blind in one specific direction, and the consequences of that blindness are beginning to manifest in anomalies our instruments can detect. The fireball anomaly, for instance, remains only partially explained. The object designated M20226A1 accounts for a large portion of it, but a significant remainder is left over. This suggests there is more to the story. Other phenomena, such as the influx of head meteorites, events at high declinations, flashes from lunar impacts, and the multi-channel signature of the surge, all point toward additional, unidentified contributors. These could be undiscovered meteor streams, temporary surges from known sources, or even simple statistical fluctuations. We do not yet have the answer. But the fact that we cannot fully account for the activity in Earth's upper atmosphere over 3 weeks in March and April implies our detection gap may be far wider than just a single hidden asteroid. This uncertainty naturally leads to some compelling questions about the future. How many other, similar streams are waiting to be found within the data from the global meteor network? How many parent bodies lie undetected, concealed within the sunward blind zone? And just how much of Earth's everyday meteoroid environment originates from sources we have never directly observed? These are not merely rhetorical inquiries. They are concrete, scientific problems that will gradually be solved in the coming years. As more data is gathered, more sophisticated analyses are performed, and new instruments become operational, the answers will slowly emerge. It is a reminder that we are at the very beginning of this investigation, not the end. The journey of discovery has only just begun. In this context, the role of future missions is difficult to overstate. NEO Surveyor, slated for launch in 2027, is poised to rewrite a substantial part of our catalogue of near-Earth objects. Countless objects that have remained invisible for the entire history of astronomy will suddenly appear in our surveys. For the first time, we will be able to directly detect the parent bodies of existing meteor streams, which until now could only be inferred through complex analysis. The initial data from this survey will almost certainly reveal new objects we never even suspected existed. This promises to be a remarkable moment in astronomy, and it is now close enough that we can begin to anticipate the profound revelations it may hold. In the meantime, the scientific community should continue doing exactly what it is doing now. This involves the careful, ongoing analysis of meteor network data, the publication of peer-reviewed research on newly identified streams, and the cross-referencing of fireball anomalies with emerging theories. Through this patient work, we are gradually building up our understanding of this invisible population by studying its effects on our own environment. It is slow and meticulous work, but it is precisely how we will bridge the gap between what our instruments can see and what is actually there. This is the methodical process by which science illuminates the unknown, one piece of evidence at a time. To truly appreciate this moment, it helps to place it within the larger arc of humanity's relationship with space. For most of history, the night sky was viewed as a fixed and predictable canvas. The stars moved in reliable patterns, and while the planets wandered, their paths were knowable. Anything that appeared suddenly, like a comet or a meteor, was often treated as an omen, a message from a realm beyond our comprehension. We have come a long way since then. We now understand that the sky is a dynamic place, that near-Earth space is filled with moving bodies, and that our own orbital environment is a complex ecosystem. Yet, we are still discovering just how much of that ecosystem remains unmapped. We are still finding objects whose existence we can only infer. In certain regions of the sky, our instruments are still blind. Science has not eliminated the mystery of the cosmos. It has refined it, narrowing it down into specific questions that we can answer with better data. What this recent discovery represents is a kind of threshold crossing. For the first time, we have unambiguously detected the influence of a hidden asteroid population solely through its effects. We now have an existence proof. The blind zone is not empty. It is populated with active objects. As our instruments improve, our relationship with these objects will become more detailed, more quantitative, and more tangible over the coming years. The two asteroids that will pass by Earth are not the central story. The 4.5 Sigma anomaly is only a piece of the puzzle. The peer-reviewed paper provides the structural core of the narrative, but even that is not the whole picture. The complete story, the one worth remembering, is about a detection gap that has concealed an entire population of active objects from us for as long as we have been looking at the sky. And it is about the moment, this very moment, when that population finally began to reveal itself through the patient accumulation of evidence. We are not reacting to something that is coming toward Earth. We are reacting to a reality that Earth has already been moving through, entirely without our knowledge. That is what this is truly about. This is the phenomenon that the scientific paper documented. It is what the American Meteor Society has been logging in its fireball data, and it is what the hidden parent body of M2026A1 represents. It is not a threat or an emergency, but a revelation. It is a revelation about the limits of what we can perceive and about how much of the world around us operates in places we have not yet figured out how to look. The sky is, and always has been, far busier than our catalogues suggest. The profound difference is that now we are beginning to know it. And knowing, even without seeing, is the first step toward true understanding. The invisible asteroid feeding Earth's skies has been there all along. It simply took a convergence of evidence, a meticulous scientist, and a fortuitous week of celestial events for us to finally notice its presence. What comes next promises to be even more fascinating, because if one such object is there, others are too. The question is no longer whether we will find them, but rather how many there are, how soon we will find them, and what they will teach us about the parts of the sky we are only just beginning to see. The next time you look up at the night sky, remember that what you are seeing is only a fraction of what is truly there. The hidden fraction, the one behind the sun's glare, the one in the blind zone, the one that has been quietly influencing Earth's environment for longer than we have been alive, is finally, slowly, becoming visible. It is not revealing itself through direct observation or any telescope we have ever built. Instead, it is communicating through the light of its own debris, burning up in our atmosphere, telling us, in the oldest language, the universe knows that we have been sharing our corner of space with something we never knew was there. Ultimately, the importance of this moment extends far beyond any single flyby, specific scientific paper, or isolated anomaly. What makes this time truly remarkable is not a sense of alarm, but a quiet, dawning realization. For the first time, we are beginning to perceive what has been present in the sky all along. The story of our universe, after all, is not found in the territories we have already mapped, but in the vast, uncharted expanses still waiting to be found. And so, the next great discovery might already be on its way, a faint streak of light, arriving from a direction we have not yet learned to watch.